Think you understand decibels? You probably don't. Not really. One thing that became abundantly clear after getting an electrical engineering degree is that most people are in the same boat. They don't really understand decibels either, including many engineers and myself at times. It's not even a true unit, at least by my definition. It's a relative ratio named for an inventor known to be a bit of an asshole, Alexander Graham Bell. This video will explain the confusion and dispel the mayhem surrounding the decibel. So strap in for a surprisingly deep dive into this terrible relative unit. And welcome to Overengineered. The decibel. It's a relative unit. And most people don't get that. People know it's typically used to measure sound, but that's about the extent of their knowledge. And they're right, but nobody understands what 80 decibels of sound actually means. A decibel only makes sense as a unit of comparison. In order to express a quantity in decibels, you actually need two measurements: the desired number and the number you wish to compare it to. I don't personally believe that the decibel is a unit by my definition of the term. And the folks at the International Committee for Weights and Measures agree with me. So the decibel doesn't show up in the official system of SI units, also known as the metric system. But the American Standards Institute, NIST, does define it. So chalk one more up for weird American standards nobody else likes. Ah well. At least it's better than measuring the length of a bridge in smoots. To me, a unit needs to define a physically measurable quantity like distance or time. A decibel is just another way to express a ratio that we named after a dude for some reason. Seems strange. If I'm coming off salty, it's because I am. The decibel creates way more confusion than it fixes. Part of that confusion is because the decibel was originally invented as a unit of convenience, and almost by accident. It was originally called the transmission unit, and it only referred to one thing, that being signal loss in telephone cables. It was rechristened the decibel by none other than the folks at Bell Labs. No relation. But those guys do seem to come up in my videos quite frequently. The invention coincided with the rise of engineering as a discipline, and use cases for a logarithmic ratio were rampant. So naturally, the decibel was misused and abused almost immediately, leaving us with the mishmash we have today. Power, voltage, sound pressure, gain, all with their own bases and definitions. Physicists be damned, the engineering approximation won the day. If a person lists a figure in dB with no letters after it, he's either expressing a quantity that is supposed to be a unitless ratio, implying some unknown reference, or he doesn't know what he's talking about. That last point can usually be assumed on the internet though. Decibels need a point of comparison to have physical meaning. This is the most confusing part of decibels as a unit. When using this unitless tool, you need to know whether the actual underlying physical units in question are relationships of power or relationships of amplitude. The reasoning for this is antiquated and imprecise. The decibel was initially used for relationships of power, meaning the actual physical principle of energy per unit time. But some engineers at the time wanted to use it for amplitude and have the relationships be directly comparable, so the decibel has two logarithmic definitions. One for power, and one for amplitude. They differ by a factor of 2. The whole point of using a decibel is to express ratios logarithmically. That's a very powerful concept, especially when the numerator and denominator in a ratio are very different sizes. Obviously, a ratio can be expressed as a single unitless number. You then take the base 10 logarithm of that number, which is also like asking the question, to what power would I have to raise the number 10 such that the result is equal to the target ratio? Taking this step turns ridiculously large numbers into manageable positive ones. Ridiculously small numbers become manageable negative ones. And because of the rules of logarithmic algebra, multiplying actual ratios is mathematically identical to adding log numbers. So you can have chains of gain stages multiplying each other and easily find the equivalent gain through addition. Massive ranges can be shown on logarithmic graphs in a small amount of space. Helpful. If a decibel were just a simple logarithmic ratio, I'd have no problem with it. But that nasty factor of 2
Smeagol hates nasty releases.
is where things go off the rails. The deci part of decibel means we multiply the base 10 logarithm by 10. Fair enough for power quantities, but for amplitudes, voltage, current, pressure, anything root mean square, we multiply by 20 instead. The reason is straightforward. Power scales with amplitude squared. When you substitute that relationship into a logarithmic ratio, the factor of 2 pops out naturally. And because decibels are relative, we don't care about any constants in the underlying physics, only how much one measurement changes compared to another. Unfortunately, this gives us two definitions of the same unit. One for power, one for amplitude. And now every user of decibels has to mentally track which physical quantity they're actually talking about or risk being wrong by enormous margins. Because logarithmic errors are never small.
This shit's gonna have nuts in it.
Sometimes this can be helpful. For instance, if you integrate an amplitude range in decibels, you just converted it to power, so the power definition can be used for the result without any division or other modification. Also, for specific cases where quantities are linear and waveforms spectrally consistent, you really can expect the power gain in decibels, defined with the 10 log, to be equal to the amplitude gain in decibels, defined with the 20 log. But those cases are rare in the real world, and it usually confuses people too much to do so. So generally, nobody's going back and forth between the power definition and amplitude definition. But everyone will be using one definition or the other for a specific quantity, and it's on the users to make sure consistency is maintained. There are many modifying letters that can be tacked onto dB to indicate a specific measurement quantity or reference level. Too many to list in one video. But I'll go through the most common uses and suffixes here. The ones you are most likely to interact with. Firstly, we have actual unitless quantities, the original use case for the decibel. Signal to noise ratio is 1, where you either use the 10 log definition to compare signal power against noise power, or the 20 log definition to compare signal root mean square amplitude to noise root mean square amplitude. For electricity, this could be power ratios of watts and amplitude ratios of volts. For sound, it could be power ratios of watts to amplitude ratios of pascals. The same units apply to decibels of gain or attenuation, but instead of comparing signal to noise, we compare output to input. Then we have acoustics, the most misused of any. People throw around sound levels in dB all the time. Because the people who design things usually know what's intended based on context, this works, but it's technically meaningless. It's like if a cop stopped an American in Canada and asked how fast he was going, and he just said 69. 69 what? Canadians use kilometers an hour, but he meant miles per hour. It's absurd. For standard sound pressure level, the relative reference the world mostly agrees on is 20 micropascals, which is the root mean square amplitude of the pressure wave. That's what sound is. So a 60 dB SPL sound is 60 dB above that tiny level, equivalent to a factor of 1,000 times. 20 micropascals is the arbitrary definition of choice because it's the threshold of human hearing, the lowest sound level most humans can reliably hear. While it's safe to assume, it could be different, and nobody would know if they just give you a decibel level. For instance, dB SPL measurements in water have a basis of 1 micropascal instead of 20. In electrical and acoustical engineering, the misuse is not quite so severe. If you see dBV in this context, it's a 20 log amplitude ratio relative to 1 volt root mean square. dBu is similarly a 20 log amplitude ratio relative to 0.775 volts root mean square for historical reasons. dBm is a 10 log power ratio relative to 1 milliwatt. dBi is a 10 log power ratio used for antennas, and it relates the gain of the most sensitive region of the antenna pattern to that of a perfect sphere, quantifying the directivity. There are many more such quantities for use in varying engineering fields with different bases. Just make sure to know if the quantity is a 10 log power or 20 log amplitude relationship, and what the reference level is when you use them. Lastly, we have digital systems, where the basis is usually assumed to be the full-scale measurement range or the number of possible states available. Decibels can be used to directly compare one digital number to another. For example, dBFS uses a 20 log amplitude scale to compare the raw digital level to the maximum possible level. So it's always less than or equal to 0 dBFS. dBTP is basically the same thing, but will mathematically reconstruct the analog waveform to find peaks between samples and evaluate those against full scale. The decibel. It's not a real unit, just a relative ratio. Power or amplitude, 10 log or 20 log, dBu or dBV. You need to know which, or you'll be off by orders of magnitude. It's a confusing system shaped mostly by historical misuse, but it's the best logarithmic unit we've got. When used correctly though, decibels can be very helpful. They turn huge ranges into something intelligible, make chains of gain stages easy, and let numbers tell a story instead of drowning you in chaos. So next time someone drops a dB number like it means something on its own, you'll know better. If you got something out of this video, hit like, leave a comment, subscribe, and check out the next videos in this series here. I've also got a Patreon page linked below if you feel like supporting my hobby. See you next time.